What we learned in the past video was that everything we tried in terms of simulating the simple NACA 0010 airfoil didn't give us the result that we should have expected based upon really well established known data for lift and drag. And what I alluded to was that there were some settings in our simulation that maybe we could tweak to make that better. So what I want to do now is go through specifically ways that we can fix the model and ultimately make it perform in a way that is more accurate. And keep in mind that this won't always work, but let's see what we can do. So here we are in Solidworks with the same airfoil we've had in the previous simulations. It has an angle of attack of 10 degrees, which according to the data from the NACA results should give us one of the highest lift coefficients, and it should give us a lift to drag coefficient based on looking specifically at the tables of a number around 22. So let's see what we can do with that. Now, this first scenario, one of the things that I've done is I've created a new goal. So you recall in a previous videos I've specified goals here. Well, I can also specify a calculated goal. And if you go and edit the definition or add a new goal, you can just simply select the previous goals. In this case, I selected the surface X drag force and the surface Y drag force and did a division of the two of them, just simply using the calculator tool at the bottom. So by doing so, I've given myself a calculated goal, which is the number that I want to test to see if this simulation is correct. So I'm going to use that in all of the simulations that I'll run. So for starters, I have a mesh definition where I've got it set at the coarsest, so the level of 1. And I also have an inflation rate of 4.5. So that means that the factor of the size of the cells at the perimeter of the computational zone is 4.5 times the size of the cells close to the middle. And you can play around with that inflation rate. It doesn't make that much difference, but certainly something worth testing. So when we do that, the mesh that I'm showing here is the mesh that we end up with. You can see it's fairly coarse. Maybe there's a dozen or so grid points along the top surface of the airfoil. And that ultimately is something we have to be aware of. The other thing that I've talked about in the previous videos is the computational volume. This is a two-dimensional model that I'm using, and that's to save computational time. But you can see that the wing here takes up a significant portion of this volume. So let's run this and see what we get. I'll do a new calculation. I won't take the previous results, but I'll just run it. And if I look at the window opens up here, I can actually plot the goals as it goes along. And you can see the solver finished. There were these oscillations in the goals, that's that ratio, and it finished up with an average value of 6.4. Now keep in mind, we're looking for 22, so 6.4 isn't there yet. That calculation worked out in 41 iterations, so it settled out at a steady value after 41 iterations, and sorry, 57 iterations, and that took 5 seconds of CPU time. So that's fairly quick. One of the important things here is that there were only 44 cells contacting the solid. So that's pretty coarse grid. Now, we can try two different things. We can play with the size of the mesh and the shape of the mesh, and we can also play with the computation volume. And we're going to do that in this video. But first, let's have a look at some of the results plotted. Here's a cut plot of the streamlines. And you can see the streamlines look like you would have seen drawn in a textbook for this. Note that up here at the perimeter of the region, there's an awful lot of angle of those flow lines, which says to me that we haven't simulated everything that is interesting in this flow field. In fact, there's stuff going on that we haven't accounted for that's affecting beyond our calculation field, and that ultimately is a problem. The other problem, of course, is the mesh size, and I've shown that already, but you can see that coarse mesh size that we're using. And if we look at the flow trajectories, then they look like you would expect given those flow lines. The flow comes into this region. There's a stagnation point, right around here, just as I showed in my cartoons, hand-drawn. And looking at this zone, there's something funny going on in here, but it's very hard to see given our flow lines. Now maybe I'll try to change some of the colors there. So now you can see that our flow lines are quite jagged, but they're doing something odd in the backside of that wing. I'm just going to go to a mesh level of 3, let's say. And I've changed nothing else. And I'll run this. I'll run it as a new calculation. And so the calculation is finished. Notice the hunting here of that ratio that we're looking to solve. It starts out relatively high, I suppose, although this scale is amplified because it picks an auto scale here. I'm going to set that to 0 actually. And because we know that this is going to be a scale that we want that should be 22, I'm going to pick 25 there. So it oscillated and it did stabilize after 70 odd iterations. It came out at a 7.1 newtons, which is different than our first run at just simply changing the grid size. So we could continue to play that game, and we could increase the grid size more.
I'm back. I bet you didn't think that I'd be back with an assignment.
And you can see that that's hunting for a solution as well. And it comes out with a similar but slightly different value again, not too different. And if we look at the fluid cells, the number of fluid cells contacting the solid, 139 in this case, and 2,600 cells, not a very refined grid. And we could continue to increase that, increase the level of detail. Now this will take longer. And look at how much it's hunting now. But it does stabilize. And now all we've done was change the grid size again, and instead of getting a value of 7 point something, now we're at 9.2. So we've changed nothing with the flow geometry, we've changed nothing with the definition of the problem. All we've done is change the grid size. So the fact that it's so sensitive to that one calculation parameter is a bit worrisome. In fact, I've done a more detailed test of this, And this plot shows, among other things, this is the target. The orange line is our target of 22. And for exactly this calculation I've just shown you, I started out with, this is plotted versus the number of grid points in contact with the boundary. So I focused on how many grid points were close to the wing. I didn't do this on the basis of how many total grid points there were in the volume. That would look similar. And you can see that as I increased the number of grid points close to the wing, certainly the calculation increased dramatically. I went from initially a number like 7.2 to 12.4. That's a pretty big change in a derived number that we're using as an evaluation of quality. And especially since 22 is the orange line, which is where we want to reach. Now, I also went a lot further. I actually really increased the number of points. This is a logarithmic scale. So I went from 340 grid points on the boundary up to almost 4,000 grid points on the boundary, up to even 60,000 grid points on the boundary. And that calculation took my computer quite a long time to complete. And even I went up to 235,000 grid points on the boundary. That's an incredibly fine mesh. And my result got nowhere near close to 22. The best I could do was 12. So that certainly helped, and that's part of the story. But it's not the only thing. So let's have a quick look at some of the plots. So the streamlines, again, you've seen this already, and they look just like a cartoon depiction of flow over an airfoil. Nothing to see here. If we look at the flow trajectories, then they're certainly finer, and there's something strange going on there. And is that causing us a problem? And then the other thing we can see is up in this region, there's a lot of activity, a lot of flow lines that are crossing our computational boundary. So there's things going on up here that we're really not accounting for, and we don't know. So by increasing the grid point size, we may solve some of the detail flow close to the boundary layer, but we don't do it in a very intelligent way, because we're actually distributing an awful lot of points that are kind of unnecessary out in this region, and we're still not getting a terribly great inflation of number of points close to the surface. So one of the things we can do to improve this is, if we go up to the mesh tool, we can insert a local mesh. And the local mesh, if we pick the surface of the wing, which is the area that we're most interested in, and we refine the cells close to a solid boundary, now if we look, you can see that it's quite a bit finer in here than it was, and not so much in the outer area. And if we run this, now we have 56,000 cells contacting the surface. And you can see that there's a big change and big hunting of the ratio that I'm using as the goal. And it seems to stabilize. But wait, no, it's increasing again as we go along through more and more iterations. So the further we go in iterations, the larger that number gets, which is curious. But the fact that it's changing in a fairly stable, predictable way is actually encouraging that this isn't a hugely unstable calculation, which is good. In some cases, when you look for goal hunting like this, you'll see the result spike up and down and move quite dramatically, even through zero. But this is behaving itself quite nicely. And there we finished, and the result. And there we finished, and the result is given us a value of 10.2, which is getting closer, as my graph showed here, getting closer to the target of 22, but still it's in this region here where we're still only half of what we're looking for that target. So we've tried refining and refining the mesh, making the grid points smaller, up to a very high number of grid points. And we certainly saw that the lift to drag ratio increased, got more realistic, and yet it still didn't get to be a correct answer. So let's look at another approach. Let's look at the computational domain. Now we can stretch that and try to get the computational domain to be something that at the borders is out where things are kind of boring. Right now I'm using an x direction in the positive x of 0.2, so that's the direction downstream, the way this is defined. And I'm going to make that 0.8. And I'll go upstream 0.4. I didn't update there. There. So now it's a fairly long tunnel, and yet we still want to go above and below. So I'm going to go up 0.5 and down 0.5. So now you can see our computational region is such that it's quite big compared to the wing that we're simulating. Why, you're thinking, would that make a difference? Well, let's just see. Before we go any further, though, we should probably have a look at the mesh. And you can see that our mesh expands further out in the field. So while we've added a whole lot more volume or more area to this computation, we haven't added that many more data points. And so that's encouraging and helpful. But I think before I go on, I might actually go in and edit the inflation rate. So this will make the grid points farther away much larger, much coarser, but there's not much going on, we hope, out here. All the action is in close to the wing. And if we look at the local mesh, I've got that set of fairly aggressively giving me fine grid points close in. And you can see the size of those grid points close into the boundary is good. Now, if we run this again, it will be a fairly long run because there's a lot of points. And you can see we've got 22,000 points contacting the solid of 48,000 points total. So we don't have that many more data points in the whole region. And it's actually progressing quite quickly. So now there you can see that we've increased the computational volume, and we have an answer that is pretty darn close to what our expectation is, which is 22 for that lift to drag ratio. And let's look at, well, we can look at the mesh, show that. You can see it's quite large mesh points out here, and very small in by the body. Just hide the mesh for now. Let's look at the streamlines. So now what you're looking at is certainly the streamlines in close to the body are similar to what we've seen before. But up here at the boundaries, things are pretty boring, mostly horizontal. And I guess we could make it even larger still, but the fact that we're simulating something where we're really catching all of the really high gradients and high velocity changes and things within the computational volume makes a big difference. Now if we look at the flow trajectories, and I'll just turn off the streamlines. And we look in closely, and you can see that for those trajectories on the boundary, they're pretty solid. There's nothing strange going on. And notice that the grid points are such that the streamlines off the tail of the surface are actually quite close together. Whereas before we had what looked like something rather odd, now we have this nice sweep up and down, which is frankly what one would expect from an aircraft wing. And we've done that by increasing the volume of our simulation. This is my collection of data from a series of runs that I've done to show you this situation. Let me just bring this. So here I've got a plot of the drag to lift or lift to drag ratio that I've calculated from multiple simulations, where I simply took a variety of grid sizes. So these points here are the points you've seen already, which was I started out at a very coarse grid, and I increased the grid size, or grid number, made finer and finer grids. So you can see that on this axis, I didn't change the horizontal axis for those, which was the volume or the area that I was using for my calculation volume. But by making the grid points finer and finer, I moved that closer to our target, which was 22. And that certainly helped, but it didn't get us all the way. What really was important to do also was properly defining the calculation volume. And this axis horizontally is literally the area of my computation area. So if it was 0.2 meters long by 0.2 meters high, then that gave me my initial. And then I just progressively increased that volume. Now, the reason that the lift to drag ratio is higher than we expected here is probably because the boundary layer wall that I chose was ideal. Zero friction, no roughness. So I did get a higher lift to drag coefficient than I'd expected for this airfoil, but at least it's in the right range. You know, it's in the 20s, as opposed to when I started, this was nowhere near what one would expect from the tables. So that's important. So we've refined the grid size, especially close to the boundary layer where all the action is happening, frankly. In the case of an airfoil, the boundary layer is what creates the lift. So we need to have a grid that simulates and basically allows the modeling of the boundary layer to happen correctly. But then there's also the large-scale bulk flow that we can't ignore. And so we need to make sure we have a computational volume that's big enough to span the area where interesting things are happening. So those two factors, if we don't get them right, even though you might get streamlines that look sort of okay, the result will be really not very reliable. So before we leave this, let's try a couple of other scenarios. So this was the scenario for having a wing at 10 degrees, and as I said, with an ideal wall. If instead of an ideal wall, we give a real wall, so a real wall with a roughness, and see how our simulation runs with that. Now, in this run, I'm keeping everything the same. I'm actually going to continue the calculation here. And that will enable us to basically speed it up and use the bulk results initially.
So, here's what I've got for you now. So there's all this evil flow simulation work to be done. In this week's experiment, because it's an experiment, you're going to have to simulate a cylinder. Cylinder. Yes, a cylinder. A round rod. Or a square rod. Just a rod. A rod. You know what a rod is. And because a cylinder is actually round and well understood, you can try and match it to real data that you'll find in any fluids book. Ah!
There, I've just stopped that calculation. It keeps on going. And notice what's happened. Now, instead of having a nice, steady, consistent result that somewhat agrees with the expectation, now all I did was added roughness and a real boundary layer condition. And what I ended up getting was this kind of jumping around, oscillating result. And it didn't look like it was going to be ending very soon. Let's see what the flow trajectory looks like in this case. So that looks kind of funny. We didn't see that before. Remember in the previous, we saw a nice steady flow line that stayed relatively low down. If we look at the cut plot, look at this. It's simulated this crazy vortex here in this strange location. And if we looked at each iteration, we would find that that crazy vortex comes and goes in odd ways, which is the reason why our solution ratio of lift to drag was going up and down and up and down. Well, this is a case where we're trying to ask a computational tool to simulate a very difficult physical phenomenon, which is the boundary layer and the behavior at the boundary layer. Now, if we could look at this simulation in real time as it moves, we would see that with each successive iteration, the location of a separation point on the surface of this wing would be different. And let's just carry on with this calculation.
Okay. round rod, round cylinder. That, my friends, is eight. No. What is it? I don't know. Let me check.
There, I'm going to stop it there. And let's have another look at the flow field. So now you can see that flow trajectory, which looked different again in the previous example I showed, looks different again. And let's look at the cut plot of the streamlines. And that's different again now too. Now you can see that that vortex in the wake has changed quite dramatically. And in fact, what we would see is that oscillating up and down of the lift to drag coefficient is essentially this feature, whatever it is, this vortex feature, spinning around and moving, and the separation point that this software is predicting is moving from right around here where my mouse is up and down the surface of the wing. The further that the separation point where this vortex forms goes towards the leading edge, the less lift we have and the more drag. Likewise, the further that separation point goes back here, the less drag we have and the more lift. So the software tool's ability to predict this phenomenon, which is fundamentally dependent upon little details in here close to the surface, is absolutely crucial to getting a correct bulk scale number. Ooh, that's interesting. There's a second vortex formed here in this calculation. Now, none of this is real. This is all calculation stuff. There's no reason to expect that what we're seeing is actually happening in the real world. So once again, we have to be very, very cautious of interpreting flow analysis results without a lot more validation and a lot more care taken to understand what they mean. So I'm going to try just one more thing. I'm going to go back to our wall, and I'm going to reduce that down to 0 microns. So making it a smooth wall, although modeled as a real wall. And let's try running this again. And we'll run this as a new calculation, mesh it and solve it. And we might as well start with the previous results.
I'm back. It's 5 centimeters in diameter. And it's stainless steel, so it's relatively smooth. And it's a flow cylinder in a cross flow. Ha! I like doing that. Scary. So, 5 centimeter diameter in a cross flow of at least 1, 2, and 3 meters per second in air. Did you hear me? Air.
And here it is going all crazy on us again. We'll just stop it there, and let's see what the result currently looks like. And so you can see that once again we have this crazy stuff forming in the wake of this real flow. And the question we don't know is this realistic or not? And you know, we really don't have the tools in the case of this model to tell that in terms of the model, except to look at the real data from the NACA foils. Now, it doesn't seem realistic that going from the real wall condition with 0 micron roughness to an ideal wall should make our calculation so wrong or so different, but it does. So that's one of the things that you have to be really aware of is those fine scale details really matter. Now I've gone back to an ideal wall, and before I finish up, I'll just do one more little change. I'm going to go back over to the features, and I'm going to try a higher angle of attack. Going to try minus 20 degrees. And with that, we'll leave everything else the same. The ideal wall now, this should give us a well-behaved solution. And we'll run the simulation. And there we have the simulation finished. And what's interesting about this one is that even though it did oscillate up and down quite a bit, it never went totally crazy like the previous one. So let's have a look at what our flow trajectories look like. Okay, so that looks like we've seen some of that before. There's something funny going on here. And there's our streamlines. Now, once again, these vortices are forming here. We know that this is a situation of 20 degrees where the NACA data tells us that this airfoil has essentially stalled. This is a case where we expect the lift to drag coefficient is quite low. In fact, I can look up the data, and if I look at the plot of lift to drag and you project that, really it doesn't we don't expect it to have really any lift at anything beyond 12 degrees. So the drag should be so high, and the reason why that drag is so high is because this wing has stalled. There is an eddy in the back side of the wing, which is destroying any chance of there being lift. And in fact, that's what our simulation has showed. So here's a situation where that back eddy on the airfoil is actually correct, and it's validated in our empirical data from experiment. We've seen it here, and yet because we also saw it in a situation where it wasn't correct, we have a really hard time telling that this is right and that was wrong, except for having the data to compare with. And so I'm going to stop there. And let's talk about where we've come with this. We started off with doing simulation of a really well-known flow device, that is an airfoil. We did it simply, and we created a coarse mesh, which looked okay. We got a result that looked like what's drawn in the textbook for flow around an airfoil. we found that if you looked more closely, though, that the numbers that were calculated by this method didn't make any sense. That we couldn't trust them, especially in terms of the lift, which is a complex phenomena that's the result of a boundary layer behavior. And so we had to look more closely and start trying to refine the mesh, which helped a lot to give us more predictable, more realistic and believable results. Certainly the results that we started to see when we refined the mesh were stable. And then we still didn't get an answer that was close numerically to what our expectation was. And that's because we had another problem, which was the simulation calculation area. The volume we were doing the calculation in was too small. The streamlines that we were creating were crossing the boundaries in uncertain ways, and we really didn't know what the true flow field was, and that was affecting our result. So those calculation problems are really, really important. And as you can tell, that if you just sat down and did one simulation, you would have maybe thought, oh, that was correct, and moved on, when in fact it's not. Flow simulation can lead you down the garden path very easily. You have to learn to be very skeptical about it, and also to prove that it's working correctly. And even in cases that are simple and you believe are working correctly, you still have to be very cautious and be very careful about proving that that's the case. This simulation that I've shown you in this series of videos would be no different if we used ANSYS or Solidworks. This is a common feature of the finite volume method and any calculation like this. So use your engineering judgment, be very skeptical, and always try to come back to a real-world scenario. Thanks for watching.